So today's session is all about like AMBA protocols. Some of you might have heard about AMBA protocol. Some of you might be listening first time. Anyone has any idea about protocols? Like, hello?
Yes, sir.
Okay. So, anyone know about protocol? Like, anyone heard before it? Like, what are the AMBA protocols and any idea? Okay, fine. No issue. Actually, protocols like AMBA protocols are the published by ARM company, and ARM company has published these protocols with some requirements. Of course, like every new thing we have, because there was some requirement, and to fulfill that requirement, company came up with these all protocols. So, company ARM has its own like ARM itself has the full form like. A has like application specific, R is the real time specific, and EM is the like embedded medium range of performance is required. So that time AIM series of protocols. So basically, like mostly we require protocols on the basis of requirement. Like there may be some scenario where we required high performing protocols, so that time AXI we used. When there may be scenario where we required medium range of performance protocols, so that time we go for AHP. And sometimes there is requirement of low power peripheral, so that time we go for APB. So with such a requirement, ARM company kept on publishing various protocols, and amongst them APB was the first one protocol published by ARM. Then AHB was published, then AXI published, and then coherency related protocols. So like that, still it's evolving. Like the with the evolving era, like we know, like in every technologies are getting updated to match up with that technology. Protocols are coming. Actually, protocol why we need that may be question you people having. So on SOC level, SOC again may be new thing for you guys, but processor might be everyone have heard. So processor itself is a SOC, and on that SOC, there are various functional blocks over there, and to get communicate between these, we need certain protocols, and that's where we use this AHB, AXI, APB, whatever the protocols we are going to learn. All of them protocol you will find on SOC level as an application point of view. I am saying so. And then let's start basically with introduction. So amba is protocol we are like saying. So amba, it's not itself a protocol. Amba is a family under which all the protocols comes, like APB, AHB, AXI, CHI, whatever the protocols you have heard till now, published by ARM company, all of them will come under this amba family. And amba itself has the full form advanced microcontroller bus architecture. So here you can see bus is the word, because protocols are nothing but the bus through which our transactions are going to be travel, are going to be transmit from one block to another block. And that is the basic usage of protocol. And this is the on chip on open stand on chip. Basically protocols can be divided in two categories, like on chip and off chip. And as I said earlier also, SOC. So on SOC there will be functional blocks, and that functional blocks are going to be integrated on chip. And to get communication, to establish a communication between these blocks, we are going to use on chip protocols. And the off chip protocol you can consider like USB, PCI, DDR. They are going to be inserted from external world. They are not going to be integrated on chip while manufacturing itself on SoC level. So that's why we categorize as on chip and off chip. And whatever the protocols like APB, AHB, XI we are going to study, that are all like of on chip type, because they will get integrated on chip itself while manufacturing itself. Then describe strategy for the interconnection management of functional blocks that make up the, like I said, like management point of view, uh, like on SoC you can like this thing we must have heard, like quad core processor, octa core processor. This thing we of course everyone knows. So in quad core it means like four processors will be there. So four processor are something which is of high performing device. We can consider them as of high performing device which is working on very much high frequency. Its requirement is high power. Everything will be high. So APB protocol is like is of low peripheral, so cannot be used for that processor. AHB maybe we can use, but since it is a octa core, or quad core 4 processor are there, so AHB will not be efficient enough. So that's why we will use for AXI. So for that processor we will use AXI from processor point of view, but same processor has to deal with peripheral also, because processor is the only one who is handling every operation on our SoC, or mobile phone everywhere. So that processor not just has to handle or deal with the low power peripheral, like high performing subsystem also it has to handle. So every subsystem will have their own requirement. So that's why we require bridges in between to establish a communication. Like a processor will be using AXI since it is of high performance, but at the same time some peripheral device is there which is of low power peripheral, so it will use APB. But AHB and APB, how will it get communicated? So that's where we will require the bridges. Bridge will convert that AHB into APB, APB into AXI, like that. Communication will be there in between on SoC layer, like that scene we can imagine basically. And then so actually this is the diagram, hope you people can see. So see here, bridge is there in between. At right side you will find out the APB protocol. Like APB protocol is been used for UART, timer, keypad, and PIO. These are all like the peripheral devices which are working on low power. And at left side, you will find out the ARM processor, high bandwidth on-chip RAM, DMA bus master, high bandwidth external memory interface. So these are of like the subs, like on SoC level, we have functional blocks. We can call it as a subsystem also. So like at LHS side, you will find out four subsystem, and all of them are working on high frequency, high bandwidth. So that's why we can use AHB, AXI, or ASB, but mostly we will use AXI nowadays. So this AXI, or let's say since here AHB is written, so let's consider AHB only. So here AHB we have, and this like ARM processor has to communicate with keypad, let's say. So that ARM processor will give its a transaction to AHB, and then AHB through AHB bus, that transaction has to go to the keypad. But that transaction will be of high performance, and keypad will be working on low performance frequency, so it cannot accept as it is. There must be bridge in between. So that's why we have AHB to APB bridge converter, and that bridge will convert that transaction of low frequency and will pass to the APB. Then APB, through APB interface or through APB bus, it will get to the keypad. Like that communication we can imagine basically. Like anyone is having any doubt here, like you people can ask any doubt in between, feel free to ask. Hello. Hello, am I audible?
Yes, sir. Yes, sir.
Am I going fast? Like you can ask in between, please be interactive so that I can know whether am I going fast, slow, you people are getting or not. Okay.
Yes.
So basically this diagram is clear, like how AHB and APB conversion is happening, and like how processor is using AHB, not APB, why keypad UART are using APB, like means how basically we choose protocol for which point of view. That point you guys got cleared. Hello.
Yes, sir.
Okay, fine. Thanks. AHB directly we cannot start AHB, APB. Okay. So screen is visible, fine. Okay. So basically till now, like we have learned, not learned, basically we have just discussed something very basic thing, like why we have protocols and what is the need to have protocols. Again, I would like to just say overview about it. Like on SoC level, there will be different functional blocks, and that functional blocks has to be communicated with each other. And to establish that communication, we have to use the protocol. But which protocol to be used? So because there are the varieties of protocol are there, like ARM, like I said, ARM has its full form, application specific, real time specific, it embedded. So means functional blocks will be having their requirement. With respect to that requirement, we have to choose, like if the block is of high performance, so we can go for AHB or AXI. If it is of low performance, then we can go for APB or APB, because APB is the one for low performance. So like that, on that basis, we have to choose which protocol to be used. And APB is the first protocol which has been published by ARM, and it is the very simple protocol, and it consumes a low power, lower bandwidth whenever kind of requirement will be there. So we can say like APB we will use. So APB has its full form like Advanced Peripheral Bus. So whatever the peripheral components are there, for that requirement we will use the APB protocol. Simpler bus protocol designed for general purpose peripherals with low bandwidth, like we have seen in that diagram: timers, interrupt controllers, UARTs, GPIOs, mean general purpose input outputs. So these are all the peripheral components which will get connected through APB. APB basically, in APB, why we are saying it's a low performance, the main thing is that it requires two clock cycle to complete one transaction, and in case of AHB it requires a single cycle is enough to complete one transaction. So it's like LHS side, we have seen that bridge, if that one transaction is going to get in one clock cycle at the RHS side of APB, but APB requires two clock cycles, so it cannot take in one clock cycle the same transaction, na? So that's why we bridge required, so that in bridge, that in next clock cycle the transaction is coming from AHP will be temporarily stored, because APB will require two clock cycle to digest that one transaction. So that relation we have to match properly through bridge, and that's how we decide like it is of low performance, that is this is of high performance. On that basis we say like on the basis of clock cycle, because clock will be the reference for every protocol, and with respect to clock only transactions are going to get managed, and on that basis we decide speed. Like if some protocol is capable enough to send the data at single clock cycle, then we can say it's efficient enough. If some protocol is sending the same transaction with respect to, with the requirement of two clock cycles, so it is slow compared to that protocol. So same APB requires two clock cycle to communicate with the slave, like if it has to transfer any data, so it will require two clock cycle. If it has to receive this data, so again it will require two clock cycle. Means for every operation which will happening in APB, that require two clock cycle. Because this question may ask like personally I faced that question, like a 25 transaction if you have to transmit through APB, then how many clock cycles will be required? As I said, one transaction requires two clock cycles, so overall for 25 transaction 50 clock cycles will be required. But when it comes to the AHB, in AHB we follow the pipelining concept, so it will just require 26 clock cycles. One clock cycle extra will be required through pipelining. That is another concept. When you people will learn AHB, you will get to know why 26 clock cycle. But let's come to the APP. We require 50 clock cycle. So this question may be there, may get asked in interviews. So, and also you have to say like why two clock cycles, so that will get cleared through state diagram. In APP we have state diagram, in like ideal phase we have setup phase, access phase. So when that setup phase and access phase comes, like there is an answer. In further slide we will see like why two clock cycles are required. Is it clear, guys? Okay,
Yes, sir.
fine. Okay. So if we talk about the APB feature, so APB has the feature of non-pipeline architecture. It is of non-pipeline type. That's why it takes two clock cycle. It is a simple interface with peripheral acting as a slaves. Bridge performance type. So HB or AXI transaction into APB, then it will be given driven to the APB slave. And its optimization point of view, we will say, so it requires very low power and very few signals are there in APB. We will see that few signals in upcoming slide. And this diagram already we have seen like why we require bridge and all. Then bus implementation. So APB interconnection can be implemented in two ways: with separate read and write data bus, use multiplexed bus to get connect with various slaves onto the bus with one combined read and write data buses, since read data and write data never occurs simultaneously. So basically this thing you will get to know after after discussing these signals. First discuss signals, then this thing you people will get to know. Like in APB, we have signals like clock and reset will be there. Of course, global signals. Reset is of active low type, but main actually signals you people can describe in a category like global signals. So global signals means clock and reset, of course, will be there. Then you can define as a control signals, and the third category will be of data signal. So in control signal, you can put address, and then selection line, enable, and p write. These are all the control signals. Basically control signals in the means that control signal status will decide what kind of transaction will be driven, and then data signal will be simply data bus through which your data will be driven. But that data, how or in which pattern it will be driven, that will be decided by the control signals. So here we can put in this three category. First category will be of like your global signals, clock and reset. Then in second category of control, you can add address, selection, enable, and write. And then in data bus signals, you can say read data and write data. So basically clock is of single bit. Clock is the reference throughout we required. Reset is again of the reference type. It Since it is of active low, so it will get active when it is of low state throughout, like whenever the operation will we have to perform, like when you will write the verification test bench for it. So that time you have to keep for first clock cycle reset will be high, then you have to keep throughout low so that operation will get performed. And then address will be there, which is of 32-bit. 32-bit of bus will be there, which is of address. And then selection will be there. Selection is the line through which you have to select, like it will indicate like slaves. Like APB is a single master, has to be communicate with multiple slaves, but at a time it cannot get communicate. It can communicate at a time only one any of one of the slave. So that which one slave, like let's say we have five slaves, one master. So amongst these five slave, with which slave that master has to communicate, that will be decided by the selection signals. Like p selections will be there, which will be high with respect to particular slave, and that slave only will get communicated with the master. Rest of the slave will not get, will be deselect, you can say basically. And enable signal will be from master side. It will say like master is ready to drive all these control signals, data signals. That status will be indicated by the from the master point of view by enable signal. And write signal is one of the control signal which will decide your write operation has to be happen or read operation. Here in APB, read write simultaneously cannot happen. It is like a single port RAM where write is one, then your write operation will happen. When write is zero, your read operation will be happening, like that. Like write data will be driven when write will be one. Your read data will be as a response master will collect when your write is zero. So like that scene you can imagine here through this signals description. Like got the anyone is having doubt about these signals? Hello?
Okay.
Cleared this signal description, or you people want me to go again, or anyone is having doubt? Okay. So basically in APB, we have the state diagram. In this PPT, the state diagram is not given. Simply it's written. So like state diagram of like three state, we can imagine like ideal, setup, and access. So in ideal state, selection and enable, like selection and enable will be the will be the control signals. So selection is the responsible for to select the slave, and enable will be responsible if it is high, so it will indicate master is ready to drive the data, kind of indication will be there. So in ideal, like ideal means it's a reset, everything will be zero. So when p selection and enable is zero, so it means we can assume that this is of ideal state. But when the transaction has to be done, that time it has to come to the setup state. So in setup state, what it will indicate, like p selection will be high, it means slave is been selected, like with which slave that master has to communicate it, that has been selected in setup state, but not yet data is driven, because we don't know, slave just selected from master side, but whether that slave is ready to accept the transaction from master side or not, that not yet confirmed. So we need to wait for the slave is to be get ready. So that's how in very next state, like from setup to access state, you have to go to the in very next state, like a set okay, like setup is in first clock cycle, so in second clock cycle itself you have to move to the access state. It can't be of third or fourth. In very next of setup state you have to go to the access state. In access state your selection as well as enable both will be high. Now master is also ready to drive and slave is also selected, but as I said, whether slave is ready or not to accept the data not yet confirmed. So from slave side, slave will indicate through ready signal. Ready signal is the response will be given to the master. On that basis master will decide, oh, it has to drive the it has to transmit the transaction or not. So slave, if it is giving ready 0, it means slave is not ready. It may be busy with another master, or like that scene can be there. So master has to wait till the slave get ready. So in every clock cycle it will check for ready signal. In first clock cycle ready 0, so it will wait. In next clock cycle ready 0, again wait. In third clock cycle if ready high, then master will start its transaction. So till the time whatever the control signal is driven in a setup phase itself, that will be extended as it is. Their status won't get changed. But write data not yet be driven, because we don't know no, like whether slave is ready or not. When slave will be ready, then only write data will be driven. But till the time whatever the control signals already we have driven in setup state, that will be retained or get extended as it is. And then in let's say like now our slave is ready, so then we will do the required transaction. Then as I said, like earlier we discussed, it requires 2 clock cycles. So basically in setup state, selection will be high but enable 0, that is in 1 clock cycle. But in second clock cycle it will move to the access state. That time selection and enable both are 1. So this is how it requires 2 clock cycle, one dedicated clock cycle for setup and another dedicated clock cycle for the enable. Then it depends on completely slave, whether slave is instantly ready, or if it is required some time to get ready. So it will get retain the time, but this 2 clock cycle will require overall maybe more than that required, but minimum 2 clock cycle will be required. And when the one transaction will get complete, again it will go to the setup state. Like okay, let's say now we have to communicate with another slave, so that p selection has to be selected another slave. So that will go in setup state. Now another slave will get selected, then it will come to the access state. It will complete its transaction with that slave. Then maybe third slave, like that it will keep going. So this is how the state diagram will work. And after the enable cycle transfer is completed, the bus proceed the ideal state. If no further transfer is required, go back to the setup state if more transfer is needed. So basically when you have to transmit 5 transactions and you have completed, no more transactions are required, then you can go to the ideal state. Like finally you will be driven 0 0, selection will be 0, enable will be 0. It means ideal state, you have completed your transaction. So like that scene, you can imagine. I know it might be difficult if someone is listening first time. So it may be difficult for them. In one go, we cannot understand. Though it's APB is too much simple protocol. If anyone is having doubt, feel free to ask. Hello.
Could you please explain it again, sir?
Which one? Hello.
Whole cycle, sir.
2 clock cycle why we required?
No, sir. Whole data transfer cycle. Ideal setup and access. Say,
Okay, okay. So see, first three state we have in state diagram. In state diagram of APB, we have 3 states. One is the ideal, second one is the setup, and third one is the enable one. So ideal means basically what you understand by ideal means nothing is happening. It is in its reset state. So reset state means like everything is 0. None of the slave is selected, not even a master ready. Like it's ideal completely. So that's how P selection and enable both are 0. Got it? Then in setup, like when we have to do the transaction, when we have to go for transaction, so that time how we will go for transaction. So we have to first make sure like we are going to select one of the slave. So through P selection line, slave will get selected. But that whether slave is ready or not, that we don't know. That we will get to know in access state. So like this, keep in mind, like in setup state, if you are entering, then from setup state to access state, you have to move in very next clock cycle. Like let's say in setup state, you are having of second clock cycle. So in third clock cycle itself, you have to move to the access state. You can't move to the fourth or fifth one. Getting that point? Hello?
Sir, here enable and access state both are same or different?
Enable and access are same, you can say. Here they have given other nomenclature, but it will be mostly access only. Even I am seeing this first time. Both are same. So selection
Okay.
and enable. Yeah, so in access state, from after setup it will move to the access state. So access state, it means like you can see enable or access means you can imagine like we can access the slave, because slave is also selected. Enable high, it means like master is also ready to give the data, but we don't know slave is ready or not. Maybe slave can be busy with another master, or maybe anything can be a reason for the slave to get busy. So we have to wait for that slave to get ready. So how slave will indicate to the master? There is another signal for that as a response we receive from the slave side, that is the ready. If ready is 1, then master will understand, okay, now slave is ready, so I can transmit the data. If slave is not ready, if it is indicating ready 0, then master has to wait till the time slave gets ready. Now get cleared?
Yes, sir.
Yeah. And if after in access state, if you have to complete 10 transaction, so you will require 20 clock cycle overall, and you will complete your 10 transaction now, and after that no transaction are left. Then again you will move to the access ideal state. In ideal state, your P selection will be 0 and enable will be 0. So like that, this process will keep going like that. You can imagine as a state diagram. Basically ideal, setup and access. Okay, so can we see the right transfer? Hello?
Yes, sir.
Okay, so see here in ideal, setup and enable, you can see. So maybe after looking this diagram, some doubt will get cleared in more efficient way. So here clock will be there, like at T1, T2, T3, you can see like at with the reference of clock passage, every operation is happening. So address, write, selection, enable, these four signals are the control signals. So here in setup phase, like I said, control signals will be driven in ideal state. In first T1, like let's see, in between T1 to T2 ideal state, they have written. Why they have written ideal state? Because P selection and P enable both are 0. Now you people are getting like how we decide ideal state, because see, P selection and enable both are 0. But here in setup phase, in between T2 T3, you can see selection is high. You can see that circular round, but enable is low. Selection is high, enable is low. It means like we have entered in setup phase. Only selection and enable signal you have to see. That on that basis you can decide whether you are entered in ideal state, setup state or enable state. So in setup state, they have shown selection is high, it means the slave is been selected. And in setup phase, along with the select signal enable, other control signals also gets asserted. Like see, write also become high, address also you have driven. So write high, it means write operation you have to perform. Address also is been given. But but in setup phase we don't have clarity whether the slave is ready to accept it or not. So in enable state, we will go in enable state, selection will be high again as it is. Like see, I said the control signals of setup phase will be extended in enable phase as well, and till the time it will be extended till the time slave is ready to accept. So this is how you can see here, like from T2 to T4, all the signals which has been asserted at T2 are extended till T4. Even in T5, till the T5 address, you can see it's been extended. So see, write one, it means we have to perform the right operation. Selection 1, it means slave is been selected. Now in enable signal at T3, you can see enable is also high. It means now we have entered into the enable state, but now everything will be depend on the ready state, whether the slave is ready or not. So here this diagram is of without wait states. That's why they have considered directly like slave is ready, and now they are driving the data. but it shouldn't be there if you are going with the if you are going with weight state, but it is of diagram of without weight state, so it's fine. But mostly without weight state only we go. So without weight state concept must be understood. Like basically difference will be like without weight state and with weight state is simple. Like master wait till the time slave gets ready, and that it understand through ready signal, through ready response signal. If it is showing one, so it means slave is ready. Like here here we can see here they have already considered slave must be ready. That's how data one they have concluded at T4 only. But here they had to show ready signal also, so that we could understand the with weight and without weight concept, but they didn't show. It's fine, because they might have considered without weight state. And for reader transfer, so basically reader transfer will be happening when write will be 0. So everything will be same from the previous diagram, but here just the difference is that in setup phase you can see write is low. It means we have to perform the read data. So you can see instead at the lower side, instead of p write data bus, here it is of read data bus, where the data one which was driven. Now we are collecting the same data from the slave. This thing you got cleared? Or anyone is having doubt between read and write transfer? Forget about with and without weight state. That ready signal they haven't shown, so we will discuss later. But here simple thing, read and write transfer, you can understand on the basis of status of write signal. If write is 1, then you have to perform the write operation. If write is 0, then you have to perform the read operation. So this basic thing you got cleared. If you are not getting anything, that also you can say no issue. I'll improve. Like if you are not getting connected with me, maybe I might be going fast, so you can say.
It's clear, sir.
Okay, fine. So you got cleared with write and read transfer.
Yes, sir.
Okay, thank you. So now here they have shown no weight state, so maybe they have given ready signal. Let's see why is there no weight signal on APB. APB is designed to implement as a simple interface as possible. Okay, without weight state only they have given, that already we have discussed, means simple. Okay, so I'll explain. With and without weight state, like from master side you will drive write data, control signals, clock, everything. But from slave side, signals, three signals you will drive, you will be collecting: read data, slave error, response, and ready signal. So focused on that ready signal. That ready signal will decide weight state without weight state concept. If you are not going to be wait for the slave whether it is ready or not, by default if you are assuming that slave will always be ready, then you will put this concept in the category of no weight state. But if you are going with, if you are dealing with weight state, and basically with weight state only we have to go, because personally I have worked on projects, so that time we had to wait till the time slave get ready. We had to wait for ready signal to get high, low, that status we had to check. And even if you guys will start working on this APB project, or will you create test bench and all that, that time you will also go with weight state only. That is what, because no weight state is earlier concept. So focused on ready signal, you have to wait. If ready is 1, then you can do your transaction. If it ready is 0, then you have to wait till the time slave gets ready. Hello, am I audible? Hello, screen is visible, guys?
Yes, sir.
Okay. Okay. Okay, so we were discussing about ready signal. So basically, ready signal, we have to keep high if,
Excuse me, sir.
hello?
Actually, screen is very small.
Okay. Now is it visible?
Yeah, yes. Thank you.
Okay. So we were discussing the concept of with and without wait states. I think without wait states I had already explained. That is like we by default assume that slave is ready, but in general it doesn't happen. Slave may be busy with some another master, so we have to wait till the slave get ready, and that indication will be given by slave side through ready signal. So that when we developed our test bench verification test bench through UVM or ESV, that time you have to write certain condition, like if p ready equals to 1, then only like that you can complete your transaction, you can further proceed. So that is what basically simple with and without wait state concept. And that write and read transfer also is done if we breach. Okay, so here basically we can see the signal. So at LHS side here, AHB slave interface they have written, and RHS side they have written master. So at RHS side you can imagine processor to be present on your SOC level, and LHS side some of the like UART or maybe your keyboard like that slave you can imagine. And in between APB we have, don't focus on breach, just consider it as a simple APB interface or interconnection is the one through which we are trying to establish the connection between the master and the slave. So master will give some data, and that data has to be driven to the slave as it is, but with the slave point of view it has to get converted. So that conversion, that maintenance will be done through APB interface. That is the APB interface main job basically, we can say. And when it comes to the verification point of view, that real-time master processor or real-time slave we cannot have, so that time we develop agents in through UVM. If you guys have learned UVM, so you must know about agent. So that as a master agent we develop, as a slave agent we develop, and through master agents driver we drive the stimulus. So stimulus we are driving or giving signals, it means like uh, clock reset we will give, then your control signals we will give, we address, selection, enable, right signal, whatever we have seen, that control signals we will be driving to that APB. And then from another slaves agent we will collect through monitor, like address we will collect, write data we will collect, but read data also we will collect. And that write and read data we will compare basically in scoreboard, and we will check what is the need to compare. We have to make sure that processor, like from our right side, whatever the data we are giving, that same data has to be driven to the LHS side, so that the whether write data and read data are matching or not. If it is not matching, it means somewhere that APB is not working properly, but it has to be worked properly. So that's where we write, that's where we make sure that in scoreboard that data, write data must get matched with the read data. So these things are there basically. So here you can see like a selection are like one hot code kind of like it, don't imagine it is like a shared or multiplexer thing. Means see, interconnection of APB will be uh, since it is APB single master and multiple slave, so there won't be any arbitration. That arbitration comes into the picture when you will go for AHP, like basically whenever there are multiple masters and multiple slave. Here we have single master, multiple slave, so no need to have arbitration. Instead of that we will have decoder, some multiplexers will be there. So basically decoder and address mapping will be there. Actually what happens, master is there, master doesn't know which slave is going to be selected. Master will just issue one of the address. Let's say you have 5 slave, every slave have its address. First slave is address 0 to 10, second slave has address 11 to 20, third slave has address 21 to 30, fourth slave 41 to 50, like that. Address is been done and master is issuing address 15. So that 15 is going to be fall in which slaves category, that particular slave will get selected, and that particular slave's selection line will be high. So it is kind of address mapping. This concept you guys are getting, or I can explain again. This concept is required. Like maybe that question can came, how what is the address mapping and how slave is going to get selected. So that this like master will issue address, and this address will fall in which category, in which slaves category. Like because slave will going to have 1 KB boundary. That boundary will be like from 0 to 1023. Every slave will have its own boundary, 0 to 1023, 0 to 1023. But master is issuing address, and that address is following in between that 0 to 1023 with respect to that selection line will be high. That work will be done by decoder. So in a setup phase, when we drive control signals and address, that signals will be captured by the decoder, and decoder on the basis of that address will make the select line high with respect to that particular slave. Hello. This address mapping concept got cleared, or do I need to explain again?
Clear, sir.
Okay, got cleared.
Yes, sir.
Okay, fine. So this is how you will make sure that which slave is going to get selected. So basically, slave will be having 1K, 1K will dedicatedly boundary. Like the boundary condition will be there. Like each slave will be having this 1 KB space allotted to it, and that space will be having address range from 0 to 1023. And in between that, if master is issuing address and getting fall, that particular slave will get selected. Now the second thing is that slave will okay, slave got selected, that job is done. Now that slave will receive the control signals, address, write data it will receive, but on that basis it has to perform the operation, and it has to give it back to master again. What it has to give back? Read data, ready, and slave error. So these three signal it will given be back. So read data will be the what, the same write data which is been driven by master. Slave error is the indication through which master will understand, okay, my transaction whether it is successful or failure. So that slave error will be the one. If it is 1, then it means it is successful. 0, it means it is the transaction was unsuccessful. And why this happens? A slave error is equals to 0. There can be various reason for it. That reason can be like maybe address mapping is not done properly, maybe for address is not matched properly, means can be various reason. That thing will be detailed, we will see later. But you can just, as of now, you can say like whenever transaction is successful, that indication will be given through slave error if it is 1. If it transaction is unsuccessful, then slave error will be 0. So this is for the master point of view, because master must know na, like master has given transaction, so that transaction is whether got successful, whether that received by slave successfully or not, or in between some corruption occurred. So that information master will get to know through slave error. And that ready signal already we discussed. If slave is busy with somewhere some other master, so it needs time to complete, to it needs time, or it want that master to keep it on hold, just be waited for 2 or 3 clock cycle. After 3 clock cycle, I'll be free from my current communication, from my current transaction, then you can start your transaction. So till the third clock cycle, it will keep ready signal low, and then it will keep high, so that till the time that master will be on hold. So this mechanism will be there through ready signal. So basically, when we deal with one of the slave, we drive all the signal from masters, but these three signals we collect from the slave: ready signal, reader data signal, and the slave response, slave error basically. And these are the basic only signals we have to deal in APB. Not too much signals are there, that's why very low, like low power. Why we say APB low power? Because number of signals are very less. So since number of signals are less, so it won't require that much power consumption basically. And since less number of signals, 2 clock cycles are required, so its speed is low compared to AHBX, that already we have seen. So, but the thing is like one more concept, bridge concept, why we required that, I like to clear out. Main bridge concept. Okay, here it is a slave. Okay, so see here, slave point of view, you can see if slave is that, so from master side, what signals it will receive? Select signal it will receive, enable signal it will receive. and address signal and write signal it will receive, address and control, reset and clock as a global signal it will receive, and write data. But what it is giving to the master? Read data only, read, ready, and slave error. That has to be there. They don't have given. Maybe this is the first version of APB, that's why. And this APB, AHB, this is the bridge concept basically. So actually, this in very short, I'll explain why we required bridge concept. So basically, like I initially said, AHB, let's say AHB we are using for processor, and one of the peripheral is there which is of low peripheral, so it of course it will use APB. So AHB, like let's say we have 5 clock cycles, so AHB will be given 5 transaction for 5 clock cycle, although it require one more clock cycle, 6 clock cycle, that due to pipelining concept. But just assume that like for 5 clock cycle it is giving 5 transaction, but here in APB require to handle one transaction 2 clock cycle. So let's say it is taking 6 clock cycle APB and just taking three transaction, but it has driven to 5 transaction overall. But how many transactions are reached to the APB? Only three. 2 transactions are lost, because AAPB is not efficient compared to AHB. Na? AHB is working on single clock cycle, but AHB is working on 2 clock cycle. So that is where, to make sure our data is not going to be lost, we require bridge in between. Like FIFO concept, we know FIFO or buffer concept. What it does, it just store the data temporarily, and whenever the slave or receiver is ready, it will give that data, but with certain delay. So that delay only will be given through that bridge. That is where we require AHB to APB bridge basically. And this is what the basically a summary if we see. So AMBA provides standard interface subsystem together, SOC, AHB, high bandwidth arbitration. This is all about AHB only. APB, if we see last line, they have written APB provides low power bus, reduce interface complexity, suitable for low bandwidth general purpose. Like these are the application basically. So main application you will find out on of APB, AHB or AXI on SOC level only. Since I said initially, it is, these are all like the on-chip protocols. And on chip means when the chip SOC gets manufactured, that time only they will decide which protocol to be used for which subsystem. With respect to that, this will get decided earlier before manufacturing. And to establish communications between two subsystem, they will use one of the peripheral, one of the protocol. So protocol is basically like general meaning of protocol we can take. It is just a set of guidelines, and that guidelines we have to follow in our SOC also, so that we can establish a smooth communications between the one of the subsystem and between two functional block basically we can say. So this is about the APB. Overview just I have given about APB. There are a lot more thing, not too many, because APB is also simple. Spec is also in spec also just like whatever we have till now discussed. These are the things only present, maybe with certain another technical terms. But yeah, overview you can get to know about APB. In further sessions we can discuss more about APB. This was just a demo session, so with respect to demo only I took it, and I try to cover all the aspects of APB. If you guys have any doubt, you can ask. Otherwise, from my side, APB is over. Or you can give the feedback also, like was I too fast, or you guys were able to catch? Do I need to be a bit slow?